What if simply rearranging or padding your struct made your program 3 times slower, even without changing any logic? This example shows how memory layout can dramatically affect performance due to CPU cache behavior. We have two structs, struct A with four shorts packed together, and struct B with two shorts in between 60 bytes of padding here. Then we create a vector of a million instances of each and loop over them while incrementing these struct members. Finally, we time how long these loops take. So think about which one of these, A or B, is going to take longer to run, and I'll explain it in a moment. Okay, now that I've given you some time to think about this, let's go ahead and run this, and we can see that it takes B about 3 times as long as A. So let's think about this. On most modern CPUs, memory is transferred in cache lines, typically 64 bytes. In struct A, all four shorts are tightly packed, likely fitting within one or two cache lines. When the CPU accesses object.A, it pulls in the nearby members, B, C, D, as part of the same cache line thanks to spatial locality. But in struct B, object.B is deliberately pushed to a different cache line by the padding. So accessing both A and B causes two memory fetches instead of one, doubling memory traffic and stalling the CPU pipeline. This demonstrates poor cache line utilization and simulates a pattern similar to false sharing, where unrelated or unaligned data ends up causing cache contention. It also highlights how struct padding and alignment, often invisible in code, can have real world performance costs, especially at scale.